Hello, people.
Hi.
Hi, man.
Oh, finally, a cheerful hello from Santosh. I'm not sure if that's a good sign. Santosh cheers up at the worst things possible. But what's been going on? I think it's been quite a while since we recorded our episode. Like, when was the last one? It was
I
more than
think
a week
it's
ago.
more than a week.
Yeah, and we remember we had like promised ourselves we'll put out like 2 a week, 2 episodes a week.
These
But okay,
promises are
yeah,
meant to be broken.
yes, precisely. Uh, but okay, so what are you guys, what are you doing these days, Chetan? So I know all of you must be busy with the your what's this thing called semester planning the courses for the coming semester. You have to fill out some
That's the
stuff.
worst thing.
I haven't I haven't made up my mind about anything. Have you
The
guys been doing any physics apart from that?
Apart from that, no. But you see, the worst part about planning the this thing, the courses for the next semester is that when you talk to other people, and mostly when you talk to the junior people, you realize that these people are so excited about taking like around 27-30 credits. They want to do everything, want to try every subject, and I don't know, all these things. And then if you talk to your own batchmates, you realize that people want to do like the least amount of credits possible. People want to do like 10 credits or something. No one wants to take any course.
Yes, and I'm not sure what is sadder, like the unwarranted optimism of these youngsters, or the complete hopeless picture we have of the world as
I think
whole.
the saddest thing is the difference. The
Yeah.
expectation is just 1 year.
Imagine yeah, yeah, 1 year of Isa does this to you. And you guys think, if you think of it, this is like technically our last. I and Chetan were talking about this some time ago. This is possibly the last year we'll be together, like the lot of us. Some of us will go out to different places for our fifth year and everything, and half of that year is like gone in this lockdown thing. So we'll probably have effectively a semester, with the gang. We should make
Hopefully.
it worthwhile. Yes. Oh. Yeah, no, I don't want to talk about depressing things. Tell me something cool. Did you read anything nice or think
So
about
I
anything nice?
haven't read anything cool, but there was this question that uh, I think someone from a junior batch asked me, and that question was, I think it was related to some discussions on how, uh, in a standard way, quantum field theories are built up or constructed in some sense, which usually is the second quantization sense, where you impose some canonical quantization conditions. So the question was why. So, like, if you think about how you construct quantum field theory in a standard sense, you want to bring together, like, you want to construct a theory of a quantum theory that also respects relativity. And the standard way of doing this is to uh, demote time to an or the position to a label like time. So what we know is that the time in quantum mechanics and classical mechanics is a label, and the states and operators, they just depend on time. It's not an operator, while the position
Yes.
can sometimes act as an operator. But in like, when we want to construct a relativistic theory, we do not promote time to an operator. We always demote the position to a label, and that's the idea behind the quantum field. So that was the
It,
question of that guy was, why do you do that, or what will happen if you promote time to an operator? What are your views about this? I have some views about this.
what do you mean promote time to an operator? So to put it in slightly different words, the basic idea behind QFT is that your degrees of freedom are no longer position or velocity or whatever. Position and time and everything, they're just relegated to, like you said, coordinates, and these do not represent the degrees of freedom of a physical system. Now you're saying what happens if I promote them to operators? I don't see how is it even a sensible
No,
question.
for example,
Like,
if you consider the quantum mechanics, non-relativistic quantum mechanics, there we like the usual way of thinking about non-relativistic quantum mechanics is in form of these states or rays in Hilbert space, and then we have
yes,
a time evolution equation for that, and we study everything. But what we know is that and this is also a very interesting thing to think about. But the fact is that we can always expand our wave functions in a Fourier series, and a consequence of that is that the position can act as a basis, a complete basis for our expanding our wave functions. And so what we know is that we can have an operator called x, which can be expanded in a position basis to write like it will follow some kind of an equation, x acting on the this like the x operator acting on a position basis gives us the eigenvalue x, but we cannot have an operator like that for time.
Yes. So this is what
that
I
is
was
the
thinking
sense
of.
in which I'm talking about time as an operator.
Right. So before you make your comments, I'll just make a small comment, nothing very profound. The thing is, so in quantum mechanics, you have two kinds of evolutions of your system. One is when you make a measurement, and that is just collapsing your wave function to one of the eigenvalues of the operator that the operator that the dynamical variable you're measuring is. And the other equation is a causal time evolution equation, which is Schrodinger's equation.
Yes.
And this has nothing to do with measurements. Schrodinger's equation is what the particle would evolve if you were making no measurement. Now, if you say that there is an operator for time too, then then there is no Schrodinger's equation, right? Because there is no causal evolution anymore. It's an act of measurement. Like you're saying that there is an operator for time that acts on my state and tells me what time my label was on. So, I'm not sure if you'll be able to allow
not
for
necessary.
causal.
Amartya, it's probably not necessary, simply because we can say that in the low energy limit, whatever equation of motion we can think of, that reduces the Schrodinger equation at low energies. So,
but precisely my point, right? There is no causal equation of motion now. What purpose does Schrodinger's equation serve if you can tell the time at which you're measuring your physical system by applying an operator to it? That's what Schrodinger's equation is supposed to tell you, right? It's supposed to.
Amartya, so one thing here is that, as Santosh I think pointed out, of course, the whatever equation we might have, it won't be a Schrodinger equation because we know for sure that Schrodinger equation itself is not relativistic. So whatever equation we might have, it will be a relativistic equation, and in the non-relativistic limit, it will be the Schrodinger equation. And we know that what that equation is. It's the Klein-Gordon equation.
No, but I thought we were in the paradigm of usual quantum mechanics where we have to promote time to an operator.
But this Klein-Gordon equation will hold true even in relativistic quantum mechanics. It won't be the Klein-Gordon equation for a scalar field.
No, that's okay. That's all right. Sure, call it. Okay, sure. Let's work with the Klein-Gordon equation. My point is just that if you promote time to an operator too, then you don't have you basically don't have a concept of a wave function anymore. There is no parameter describing the evolution of your state.
as Amartya said, one thing is that the Schrodinger equation, suppose I don't make any measurements on the wave function, the Schrodinger equation, I can always predict the wave function perfectly deterministically. Now the problem is that once I promote time to an operator, I'm trying to think of some mechanism, some sort of determinism in the future or something of time evolution. Is that even possible?
Yeah, that's exactly what I said. Right? You're relegating time evolution to a measurement. So there is no notion of a causal evolution left anymore.
Okay, yeah, I think yes, I remembered what I was trying to talk about, and this was,
okay.
I think Santosh reminded me of that, and okay, I think I again lost it. Oh yeah, I realized. Yes, so the thing that
Hold
I was
on to it.
talking about is, yes, I have it now. Okay, so the thing that I was trying to talk about is that there is this very interesting misconception that a lot of people have, which is related to non-determinism in quantum mechanics. A lot of people, when they talk about quantum mechanics, like especially in pop science, this word is thrown around a lot. That
Yes.
Quantum mechanics is non-deterministic, and because of that, you should buy my spiritual healing or something. Which was like, yeah, some quantum healing or something like that. Some very
Deepak Chopra.
Deepak Chopra, yeah. So one thing here is that in like the dynamics or at the level of equations of motion, quantum mechanics is a very deterministic theory. The time evolution of the states is perfectly determined by the Schrodinger equation, and there is no non-determinism till this point. like in some
Yes.
way of saying that. Of course, we are not talking about chaotic systems and stuff like that, because that is a different kind of non-deterministic nature. But like especially at some level, quantum mechanics is a very deterministic theory. But the non-deterministic part or the probabilistic part arrives when we talk about this measurement business,
Yes.
where
Yes.
where we have to, where the wave function or whatever, this collapsing business has to choose between one of the all possible eigenvalues it can collapse into. So that is a very
Yes.
like popular misconception about quantum mechanics. And
Yes.
if you guys have to make any comments
And
about
even then, quantum mechanics is statistically deterministic. I mean, when you say deterministic, you don't have to mean that it tells you exactly what will happen. I mean, I don't see how is it any different from, let's say, statistical mechanics. Instead of giving you a precise one sure short answer, it gives you a statistical answer. And I don't, basically my point is I don't agree with people saying that this statistical determinism is different from, like the determinism of classical mechanics where you get a precise x of t.
I
And
think so.
Bohm's, so do you guys remember Bohm's pilot wave theory? Not remember. I mean, have you guys seen it?
Yes, yes.
Have you heard about it?
No, no,
That's
no.
very
Tell us.
that's very elegant. That's something. So it basically, I think it's best to just motivate it by an example. So let's say you have your double slit experiment, right? And the usual what you do in quantum mechanics is you see that once, if both the slits are open, then the electron sort of diffracts between there's an interference pattern, and you don't expect that if electron is a particle, so you conclude electron is a wave and everything. And now if you make any attempt to like measure the electron's position, you lose completely the interference pattern. Now Bohm basically said that it's not that the electron's trajectory itself is non-deterministic. It's just that the initial conditions are completely random, like completely arbitrary, and we do not know them well. And it's like a hidden variable theory. We do not know what the precise initial conditions were, and there's a set of them, and each gives rise to various perfectly well-defined classical trajectories, and it's their interference that we see. It's something on those lines. I have not seen the mathematics of it, because I remember I talked about this to Sunil Mukhi, and I well, you guys can probably guess how it turned out, but yeah, it's fairly nice.
Yeah.
Yeah,
So
so there in Bohm's theory, it's perfectly deterministic. Like the non-determinism comes from the fact that we don't know the initial conditions precisely. It's like a hidden variables. Once you know the hidden variables, everything you
but Amartya, there is one thing that I think Bell's theorem, what it shows is that you cannot have a local hidden variable. So
know.
whatever, if
Yes,
that
yes,
hidden
yes,
variable is present, it has to be non-local, which is something that troubles me a
yes,
lot about these hidden variable kind of theories. And
yes,
another thing here is that so like for a long time, like still I have this opinion that we should like spend a lot of time not thinking about these philosophical aspects of uh, at least physics, and maybe spend more time actually studying like the theory in a better way. Because usually what happens is that, like especially with young people, that we read a bit of the theory and then we start to think about the philosophical aspects without knowing the theory like at least reasonably well, and then we
yes,
might get stuck in a rabbit hole just discussing quantum gravity after just studying one page of quantum mechanics. So these are the things that sort of uh, we should like in my opinion be aware of. But that
yes,
that doesn't mean that we should not discuss these philosophical aspects. I sometimes find it very interesting to talk about this. And also another thing is that I used to be, so for a long time, so I think the two major interpretations of quantum mechanics are this Copenhagen and I think pilot wave theory or
yes,
something.
yes, yes.
On
Copenhagen
many,
and
many worlds.
Einstein's realism thing, Einstein's thing,
There is a
where
many worlds interpretation, if I remember.
Many worlds is nice. Many worlds is also nice.
So
Yeah, so there's Copenhagen, which is the widely accepted. Then there's Einstein's thing, where it says that the wave function was exactly where it was when you measured it, before you measured it too.
so this
And
pilot
then
wave
there's
thing.
this many words. Is Einstein's the same as pilot wave?
Einstein used to talk
I
about some hidden variables, I think. So I think it might be.
yes, yes. Again, so I gave up on that, but sure, go ahead.
So like one thing is I never think about these interpretations of quantum mechanics because I feel that I don't know a lot about this business. to even have an opinion about it. So like whatever vague stuff I knew about it, I used to be inclined towards this many worlds interpretation because it seemed somewhat easier to uh, think about even in an abstract sense. But recently I read some article which sort of made me shift my interest toward this pilot wave boom theory. And I think I find it interesting because it's somewhat related to some things that I have read earlier in a different context, and maybe we'll talk about it after some time. But it's a very interesting thing. It sort of convinced me that maybe that Bohm theory might be onto something, because I had never seen any mathematical basis for that pilot wave theory. So I used to think that it was maybe some kind of crap invented to it sort of seemed somewhat correct, but I had never seen any mathematical basis for that.
No, I think Bohm predicted. I think Bohm calculated the exact interference pattern from his hidden variable theory. I think the questions are still philosophical. Like the doubts are still philosophical. I mean, Bell's program put an end to local hidden variable theories, but again, like the question of locality is, arguably just a philosophical question. It would be nice.
Yeah. So
But,
okay.
yeah.
So
Your original question.
yes, about the operator of time. So the answer that I told that guy was that the reason why we prefer demoting this position operators to labels is because it is much easier to deal, or that is a much more simpler framework to construct a theory, which is the quantum field theory, rather than promoting time to an operator. Because uh, one thing was that if we promoted time to an operator, let's forget about all this physical idea about what will happen if time was an operator, like the kind of questions that you were posing, that about causality and stuff. What if I just forget about it for 10 minutes and see what will happen if I promote time to, say, a Hermitian operator? And so I'll correspondingly have to promote have a operator called the the Hamiltonian, which will be its together with the Hamiltonian, the time will have to satisfy some kind of these canonical commutation relations, which is in some
Yes.
sense T and H commutator is I. Now, what this equation shows you is that this Hamiltonian, it will have for one an unbounded spectrum, and for the second it will have to be some kind of a continuous variable.
So two things. When you write down, when you say you have a commutator for T and H, do you already have in mind some constraints like your theory being invariant under time translations or time reversal or something? Because for example, if I
I'm not
remember
sure about time
correctly,
reversal.
the XH commutator, like we usually make it 0 or whatever because we argue that our theory must be translationally invariant.
Right.
Yeah.
No,
So
so
how do
of
you
course it
write down a
won't be
commutator?
time translation invariant anymore, I guess.
Okay.
We can think about it for I think there is a way in which we will be able to make it time translation invariant. But like if we even forget about that, if we just look at this commutation relation, canonical relation, what it tells us is that if you can somehow in a very convoluted way construct a, a relation like that, where the time and the Hamiltonian satisfy this commutation relation, Hamiltonian has to be unbounded.
I see.
Right.
So but maybe okay. What if you write down this quantum field theory in curved space? Like so our usual curved space intuition tells us that there is no. It tells us basically the same thing. There is no time translation invariance. There is no
Yes,
conservation invariance.
that's why I said that we can probably construct. So I know.
Yeah.
Okay, so there is some kind of a construction where we do promote time to an operator, and as you said, it happens in, if you treat this curved spacetime. If you talk about a quantum mechanical particle in a curved spacetime, just in a single dimension. So in 1+1D, if you have one spatial and one time, or in say 0+1D, where you just have a time. So if you
Yes.
think about a relativistic quantum mechanical particle in these
Yes.
kind of low dimensions, you'll
Yes.
of course have to, like, the standard way to do those is to promote time to an operator. But now the problem is again, if the time is an operator, we know that in relativistic theory, different observers cannot agree upon the notion of a time. So
Yes.
what is the time that you're talking about here? So well, of course, we have some kind of a time which is the proper time. We can use that to construct our theory, or the Lagrangian at least. And the problem here is that this proper time, as we know in relativistic theory, is not like it has some kind of redundancy, that there can be, we can choose any affine parameter as the proper time
Yes.
along our word line.
Yes.
And so since we can do that, there is a large some kind of a gauge redundancy here, and we need to account for that when we are constructing that theory. So the standard way of looking at this relativistic particle in I think 1+1D, where you promote time to an operator, has to account and I think it does account for this gauge redundancy that you have. So this is one thing. Now the other thing is that even if you promote time to an operator, so I think someone brought up on the idea of it will break causality, I think.
Yes, I was about to point that out, Chetan. You see, if time, one thing that relativity respects is causality. If time can be stretched, squeezed, but it just cannot go backwards, to quote Interstellar. Now the point is that when you promote time to an operator, I can end up actually having two different measurements of time. I mean, in two subsequent measurements of after some spaced out measurement. Now the point is that if one of these times that we measure, they can be made, there is a probability that I get a time that violates causality, right?
So one thing is that okay, so one thing that I would like to point out here is that this is also a question that I had when I was thinking about this question, is that it's not very easy to see whether a theory is causal or not. So okay, so I'll give an example. For example, if you think about this quantum mechanical particle in 1+1D or 0+1D, where we are promoting time to an operator, it's like we can sort of comment that maybe the theory will not remain causal if you do that. But what it actually turns out is that the theory does remain causal, because the canonical momenta, so when you quantize this system, the canonical momentum to this time variable, that will vanish. So what the equations of motion of the system tell you is that the wave function do not depend upon the proper time in the system. And now,
wait, so I have a question now. So
yes,
if the canonical momentum of time vanishes,
which is
then how
Hamilton.
is it even, then okay, commutated with the Hamiltonian vanishes.
No. So the canonical momenta to the time component is
Time is
Hamiltonian.
Hamiltonian.
It's P0, right?
Right. So the Hamiltonian vanishes. No, but okay, let's forget what the Hamiltonian is. If P and P dot are, if Q and P are, I mean, if P is 0, then Q and P always commute. How is this even a quantum theory?
No, so what it tells you is that the wave functions don't depend upon proper time. So it's like this, if you talk about the electromagnetic field. So if you write down the electromagnetic field and you look at the, if you write down the field theory for electromagnetism, look at the various commutations, or if you just look at the equations of motion, what you will realize is that the P0 component, which corresponds to the 0th component of the vector or the scalar potential,
It has
it
no
vanishes.
kinetic term.
So
No,
since
so
the Hamiltonian corresponding to the A0 vanishes, it means that whatever your equations will be, the electromagnetic for the electromagnetic field, it cannot depend upon this A0. That's why we have the gauge freedom to set A0 to 0. So that's why we set A0 to 0 at our, so in the, like the standard way of saying that is that in your initial Cauchy slice that you have.
Right. No, that's okay. You can
there.
set A0. Yeah, you can set A0 initially to anything, and you can be sure
Yes.
that it's not going to evolve because the Lagrangian has no kinetic.
That's why we just set it to 0, because it can be anything. So like the easy thing to do is set it to 0, because it won't evolve. So that's the
right. No, but I thought that in this theory the only operator you have is time.
No.
And
You have time and space, all these operators. So we promoted time to an operator rather than just devoting the position to.
I see. Okay. You have 4 operators basically.
Yes. So one thing that we'll realize is that this Hamiltonian corresponding to this proper time vanishes, and so the theory cannot be a function of proper time. And then what we'll observe is that this canonical quantization, the momenta that we have, these will not be independent. So this is related to how we deal with the canonical quantization of a quantum field theory. What we realize is that the momenta that we have, these are not independent anymore, but they are constrained by this on-shell condition that
Yes.
P mu is equal to m square. And that is where
Yes.
the idea of causality of the theory is, that we'll have this restriction, this on-shell restriction.
Yes, because that's purely a special relativistic dispersion. Like that's the relativity bit of it.
Yes. So, and this will show that our theory is causal now. And the way
I see.
we can look at why it's causal. So that's one thing. So one thing that a lot of people, when they kind of rush towards studying quantum field theory. So thing that you see in a lot of places is that, especially in junior batches, is that people want to just start studying quantum field theory early on without looking at various aspects of quantum mechanics. So the thing that they miss out is why relativistic quantum mechanics is not a good theory. Why do you have to go to a field theory rather than just
Yes.
construct a relativistic quantum mechanical theory?
Yes.
And
Yes.
and the thing here is that relativistic quantum mechanics has a lot of problems. One is that it cannot account for these particle creation annihilation, because
Yes.
it's always a quantum mechanical theory is always like defined for a fixed number of particles that we have. Of course, we can construct some kind of a convoluted way in which we can account for those particle creation annihilation by dealing with harmonic oscillator kind of things. But that will just be, you will realize that what you're doing in those cases is just constructing a second quantized field theory. And
Yes.
the other thing is that relativistic quantum mechanical theory doesn't account for causality. So it's a non-causal theory. It breaks causality. If you calculate the probability that a particle can be found outside its light cone in a relativistic quantum mechanical theory, you will find that it is non-zero. So
Yes.
it's I think
Well, but technically the propagator vanishes. The propagator vanishes even in quantum field theory. It's just that you now have a different interpretation for what you mean.
No. So the propagator vanishes in quantum field theory, whereas in the quantum this relativistic quantum mechanics, it does not vanish. It is non-zero.
No, sorry, no. The propagator outside the light cone does not vanish in quantum field theory. It's
It
the
vanishes.
commutator of the commutator of the propagator. Like the commutator vanishes.
Yeah. So that basically tells you that there is, so that is the amplitude in quantum field theory, right?
Yes.
That is the amplitude.
So basically, phi of x, phi of y doesn't vanish, the expectation value, but the commutator of phi of x, phi of y vanishes.
Exactly.
That is probably what you meant.
Yeah, that's exactly what I'm saying, right?
No. Yeah, what you're saying is correct. What I'm saying is that the reason why we go to a field theory is because the amplitude in a field theory is defined that way. So what you find out that in a quantum field theory, your amplitude, however you define it, it will vanish in a relativistic quantum field theory. Whereas if you like in the standard way of doing quantum mechanics and relativistic quantum mechanics, the amplitude will be non-zero. So the thing that happens in a quantum field theory is that the contribution from the particle going like the propagator for a particle or the amplitude for a particle to be found outside its light cone is cancelled by the amplitude for its antiparticle going backwards in time, something like that.
But you have to be careful about things like this, because the causality is also true for a free bosonic theory, like not a complex scalar field, just a usual scalar field, and there is no notion of an antiparticle for just partial pi squared.
I mean, there is, like, it is its own antiparticle in some sense.
No. So from what I understand, what happens is your expectation value of phi x, phi y does not vanish outside the light cone. But then you realize that this is not a measure of what you mean by causality. By causality, you mean that the measurements that you make outside the light cone, two independent measurements, they should not interfere with each other, and so the commutator vanishes. So it's not that the propagator in itself, it's still, I mean, it's exponentially decaying outside the light cone, but it's still non-zero. But then in your relativistic quantum field theory, the problem is this propagator is what represents causality. Now, once you go to quantum field theory, your interpretation of causality is different. Now, your interpretation of causality is now in terms of measurements made by these field operators at different points.
But that has to be the definition for causality, right?
Right. No. So okay. Then the point is, in quantum mechanics, the propagator does not vanish, and you think it's troublesome with you get into trouble with causality because quantum mechanics offers no other way of defining causality.
Exactly. So that was my point. That relativistic quantum mechanics is in some sense incomplete. So it
Yes.
So basically, what you
offers
guys
two
are saying is that in quantum field theory, we have another choice of what actually causality means. And we can exploit this choice to redefine causality as expectation of the commutator instead of expectation phi of x, phi of phi. Is that what you're
Yes, a
saying?
more
I think
a
that's
more appropriate choice.
uh,
Like we have a
maybe
more
a better way
accurate
of saying.
representation of what causality means.
So Santosh, maybe a better way of saying that would be that quantum field theory, the we have another way of accounting for measurement rather than causality, because causality is like we cannot debate upon what causality is, but we can always talk about what actually constitutes a measurement in a field theory versus in some quantum mechanical particle theory. So
Yes.
since the measurement in a quantum field theory is defined that way, of course we'll find that the theory is causal. So the point was that corresponding to that, what we'll find here is that the theory still is causal, where we have the time as time as an operator, because again we have this Marshall condition, and you'll see that it will also obey same kind of computation relations. So if you calculate these amplitudes, you will find that these will vanish outside the light cone. So that is the proper way of looking at whether a theory is causal or not.
Yes.
So that was so the thing that I told that guy was that it's like the reason we don't promote time to an operator usually is because it leads to all these problems. So it's like it's not very straightforward as we would expect. Like we'll have to
Oh,
think about all these issues, and so that's why we just like demote our position to labels so that we can construct a field theory, which is a much easier framework to deal with.
I see. So I mean, I've not thought this through, but just expanding on what Santosh said about causality. I think another problem is that if you're like promoting time to an operator, and now let's say you have this notion of measuring something on your state, and then you get the time, like it returns you the eigenvalue of time. Now, now clearly, this is if we're in the framework of quantum mechanics, there has to be some kind of probability distribution associated with it. And let's say you have two possible eigenvalues, t1 and t2. Now, if you're to define some kind of time ordering between them, that is to say that there is a linearity to time, that t2 always comes after t1. Won't you just lose it here? Because now it's a statistical thing. Well, the first measurement you made was t1. Now you're not sure that the next measurement is going to be t2.
Sure. I think so. One thing is that, of course, we'll have like okay.
You lose the linear notion of what time means as a evolution, right?
I'm not sure about it because uh, yeah, like I think I'll have to think about it. I'm not very sure. But one thing is that we have a similar thing even in field theory. So even in field theory, we do not lose this notion of linear notion of time, that time always increases. So I think we can make a similar kind of like the way we think about it in field theory. I think it should be something similar in this case also, and I think it makes sense because in a field theory, of course, what we find is that the negative energy solutions, in some sense, what we have, they can be thought of as antiparticles traveling backwards in time. So
Yeah, yes.
no, I think
You know that it's imprecise.
that is actually the good way of thinking about it. Like I don't see why that's a bad way of thinking about it, because one thing is that like a lot of people seem troubled with this notion, and I don't understand it because we demanded
There's
like
no trouble. Nothing is
we
traveling
wanted a
backward.
relative theory, right? We wanted something that has space and time on equal footing. So this notion that something is traveling backwards in time should not be troublesome at all,
No,
because
no, it's
No,
not
that's the
troublesome. It's
point.
not troublesome in that sense. It's not troublesome in that sense. It's troublesome in the sense that there is nothing actually going forward and backwards in time. So it's just misleading.
no, it's going forward and backwards in time in the same, like it's going backwards in time in the same sense as something is going forwards in time. It's the same
No,
thing
but
for an antiparticle. So that's what the CPT theorem tells us. That if that this time reversal, if we think we can think about this antiparticle as a time reversal, time reversed and whatever charge conjugated and parity reverse thing. So it is the same thing. Like
that's okay. But like when you write down, but when you write down, for example, your field expansion at a given like at some xt, so you have e to the ipx with creation, e to the minus ipx with annihilation operators. At this level, there is nothing going forward and backward in time. It's just a function. Like
sure,
there is no notion of particle yet.
yeah, sure, there is none at this point.
Right. It's a good way to look at Feynman diagrams, in my opinion. That's all there is to it. I mean, it's a nice mnemonic.
Yeah, maybe. But I find it like
And-
I don't find it very surprising to even interpret it like that. Of course, then we
One
can,
more thing is that I think I'll have to take issue with the fact that we say that in relativity, space and time are on the same footing. They are not actually.
huh?
Number one, they're
We've
not
had
on
this
exactly this.
No.
They're not on exactly the same footing. For number one, there is this negative time signature. That's the negative sign in the metric.
But Santosh, I think we talked about this. No, that this negative signature is like it's not something like that's uniquely special to time. Anything that has a negative signature can be thought of as a time. That's what we discussed in one of the previous episodes. That there is
That's
nothing
true.
special about one of the coordinates that is the time. But what we know is that one of the coordinates has to have a negative signature. We can call that the time.
Right.
but I think we've again overshot our original uh, plans to keep it under 30 minutes. But yeah, that's okay.
Okay, then bye bye.
Yes.
See you guys. Bye bye.
Bye bye.